Thank you very much for having me, everybody. Thank you, Ash, for organizing. So yeah, I'm going to talk a bit about sort of a talk in two parts, and I'm not going to try to make it appear that they're both closely related, but I'm going to talk about a few different topics. I'll start by talking about some of the recent work that my lab has done on adversarial examples, and then I'll switch to some different stuff, and I'll talk about what we're doing with what we call thinking systems for logical reasoning. Okay, so to begin with, what is an adversarial example? I think many of you are probably familiar with this. It is known that, for example, if you show the ImageNet image on the left here to ResNet 50, it will think that there's a 28% cat, but it is possible to make very small perturbations to the pixel intensities of an image. So you grab onto a pixel intensity and you wiggle it either up and down. You choose the direction to push it either up or down, whichever direction makes ResNet 50 less confident that this is a cat. And with each pixel individually, you can only change the output of the network a little tiny bit. But if you have 1 million pixels to work with and you wiggle all of them, you can do things like this. You can create an image that is a small perturbation away from this original image, but ResNet 50 is 97% sure that this is a traffic light. So these kinds of simple demonstrations against what I would consider toy systems. So for the most part, image classifiers are toy systems. These simple demonstrations against toy systems, you see them all the time in the literature, and I think most of the adversarial literature focuses on these kinds of toy systems. But an interesting question is, how far can these attacks go? Is it possible to scale them up to work against more sorts of more sophisticated systems that tend to be used in industrial settings? And so I'll talk about a bit of the work that we have done in that direction. So one of the things that we have been interested in is physical adversarial attacks. So adversarial attacks where you actually make changes to a physical object in the real world, and you want to make those perturbations in such a way that the adversarial patterns will survive the detection process and they can actually manipulate realistic systems. So this is an example of me standing in front of a classroom in the Uribe Center at University of Maryland, and you'll see that there's blue boxes around all these students standing behind me, but there's no blue box around me. So this is running the YOLO detector. This is a YOLO 2 detector, which detects people, among other things. And it can't see me, even though I'm standing right in the middle of the image, because I'm wearing this strange looking sweatshirt. And it's very specifically crafted adversarial patterns on it. So how do we create these adversarial patterns? We actually train the adversarial pattern, kind of like you would train a neural network. So we got the COCO data set, which is a large object detection data set. And we load images up, like this image here from COCO, and we run it through a forward pass of the YOLO detector. And the YOLO detector outputs a feature map. We call these the objectness scores. And it has these dots that look red when it's fairly confident that there's an object to be detected in the image. And so after we detect all of these objects, we then render these adversarial patterns. So you see these adversarial patches are rendered over the detected people. And then we do another forward pass with this modified image. And now you'll see that there are less red dots in this image because these adversarial patterns suppress people. And then we use a gradient update to update the pattern to suppress the presence of all of these people as much as possible. So I compute the 2 norm of this output feature map, and then I backprop that 2 norm all the way to the pixels in these adversarial patches, and I make an update to the pattern in the adversarial patch. And when we render these patches over the people, we use this random perspective change deformation, a little bit of random noise, a little bit of random nonlinear crumple to simulate the fact that the fabric doesn't stay totally flat, a little bit of random color perturbation, and other things to sort of simulate what might happen in the real world. And so by looping through the entire COCO data set and making updates to this pattern to suppress all of the people against all of the backgrounds in the COCO data set, we can make a pretty effective adversarial pattern. And now you might think that this adversarial pattern, maybe the reason it works is just because it looks so strange. My sister told me the reason this works is because the computer thinks my sweater is so ugly that a person would never wear it. But I set out to prove that my sweater is not that ugly. And so we did a bunch of experiments, and it turns out that standard strange patterns do not easily suppress object detectors. So here's an example of that. There's a person wearing a camouflage outfit that mashes them into their background. So it's very difficult to see this person, but the YOLO detector actually finds this person just fine. In fact, camouflage is not a very effective way to evade an object detector. And here's an example of me holding an adversarial poster in front of myself, and it detects other people in the classroom, but not me, because I'm holding this adversarial poster. And interestingly, if I just flip this poster upside down, then it can detect me again. So it's not just that there's a certain pattern of colors and shapes with a certain frequency that will confuse the detector, because if you just turn this pattern upside down, it's no longer adversarial. There's a very specific adversarial pattern that exploits properties of the YOLO detector in order to make this phenomenon happen. So that's an example of an adversarial attack in the physical world. We've also been interested recently in adversarial attacks in the digital world. And we're interested in things like high-frequency trading is something that we've studied. Can you make adversarial attacks on high-frequency trading systems? Can you make adversarial attacks on things like copyright detection systems, like YouTube's Content ID system? We've studied those sorts of things in the past. Our recent focus has been more on this dataset privacy direction. And the idea behind this direction is that there's all these situations you hear about where people are scraping information from social media websites that you might not want them to have access to. So for example, here's my LinkedIn page. I think Facebook usually gets a lot of a lot of heat for leaking information, but actually I think the worst website is probably LinkedIn. If you look at someone's LinkedIn page, you get all sorts of information. You get a photo of them, you get their name, you get where they work, and oftentimes you get the rough location in which they live. And there are companies that scrape this information and then use it to sell identification services. One of those examples, one of those companies would be something like Clearview AI. And I think there's a lot of companies doing what Clearview is doing. This is just one that has gotten more media attention than the others. But they scrape your personal information and they sell information about your identity to private companies, oftentimes shady political organizations. And Clearview has actually known to have contracts with various organizations on the alt-right that they were working with, law enforcement agencies, and then interestingly, foreign governments. The CEO of Clearview has actually publicly stated numerous times that they don't sell US identity information to foreign governments, but then there was an information leak from Clearview about a year ago where it actually turned out that they were selling this information to foreign governments. And so an interesting question is there a way to poison these data sets using adversarial methods so that they're effectively useless, so that if people were to scrape this information from the web, it still wouldn't be particularly useful for them? And maybe this is one mechanism that we can use to combat this sort of scraping. So let's start with an example. Let's look at what is sometimes called in the literature untrainable examples. So there's a few methods for creating untrainable examples, which means images that you can't really train a neural network on, or at least it's very difficult to train a neural network on. And this is currently the state-of-the-art method of using adversarial examples. Okay, so let's look at let's do a little bit of a thought experiment here. Suppose that I want to train on adversarial examples. So I'm going to start with an input space. So this is Rn. This slide represents Rn. And we've got cat images. Cat images live in Catland. That's one region of Rn. And then frogs live in Frogville. That's a different region of Rn. And if I want to make an adversarial example, what I'll do is I'll take this cat image and I'll add an adversarial perturbation to it to scooch it over the boundary into Frogville. And I can take this frog image and I'll add an adversarial example and I'll scooch that over the boundary to Catland. And so I've took these fuzzy images here. In reality, they wouldn't look this fuzzy, but I've put a little fuzz on them so you can tell that they're supposed to be adversarial. And now I'm going to throw away the original images. All right, so I have these adversarial examples. I have a frog living in Catland and a cat living in Frogville. And the question is this: if I want to train a neural network on these images, what label should I assign to them? Now, a human might look at that frog and think it should be labeled frog, but there's a problem, which is that that is in a location that ResNet 50 believes should be assigned the label cat. Now, typically, if you do something like distillation of networks, what you'll do is you'll sample, and a neural network implements a function. It's a function that maps x's onto y's. When you do something like network distillation, what you're typically doing is you take a bunch of XY pairs from one network, like ResNet 50, and then you train another model like ResNet 18 to replicate those same XY pairs. So it maps the same X onto the same Y. And when you do that, the model that you've distilled onto, so like ResNet 18, might acquire the same decision boundaries as ResNet 50. And so what happens is something a little bit unintuitive. If you want to train a neural network on these adversarial examples, you should label this image as a cat, and you should label this image as a frog, because this image is in the region that you want a convolutional network to label as cats. And this is in the region you want to label as frogs. And that's a little bit unintuitive, but that's how you should label these images if you want to train a neural network that replicates the behavior of ResNet 50. So here's an example of that. This is from CFAR, so this image is a little fuzzy. I'll show an ImageNet example later. But here's a base image on the left. That's a clean image. And there's an adversarially perturbed image on the right. This adversarially perturbed image lives in catland. And if you want to train a neural network on this image, then you better label it as a cat. If you label this as a frog, a network will be very confused because there's things in the cat region that have the wrong label on them. And you might think labeling on these sort of seemingly wrongly labeled images is bad, but actually if you train only on these perturbed images, that to a human, they have the wrong labels, because to a machine, they all have the right labels. They all lie in all these images say lie in the cat region of ResNet 50 and they're labeled as cats. So if you train on these images, you actually get back something with ResNet 50-like decision boundaries. If you train on these perturbed images and then you test on clean images, you get a confusion matrix that looks like this. So it's basically a diagonal. So even though it's only been trained on images that a human thinks are labeled wrong, so things that to us look like frogs but are labeled as cats, even though to a human, it seems that all the labels are wrong, when you train on these images, you're actually distilling the decision boundaries from the original ResNet 50 onto a new model that you're training, and you can get back decision boundaries that classify clean images correctly. So you get a pretty high performance model, even though to a human, it appears that all the images were labeled wrong. Okay, so now we asked a different question. How would you make untrainable data? How do you make data that a neural network can't train on? So I just showed an example of how you would create images that appear to be labeled wrong to a human, but to a computer, training on them is just fine. They appear to be labeled correctly to a machine. And so what we really want with untrainable data is I want data that appears to be just fine. It appears to be unperturbed to a human. So it's labeled correctly to a human, and it's labeled wrong to a machine. So what I'll do is I'll take this example. We said that to train on these images, you got to label this as a cat, and you got to label this as a frog. Let's just swap those labels. Now to a human, these images are labeled correctly, but to a computer, the labels are wrong. If you try to train a neural network on images like this, it's like you're training on images that have random labels. You're training on images where all the labels are incorrect. And if you train on incorrectly labeled images, you would expect to get a very poor performing classifier. And that's actually exactly what we get. So here's an example from ImageNet. This is one of the our untrainable ImageNet images. So to a human, this is labeled as a hen. And if you want to train a human, you want to tell them that this is a hen. But to a machine, they see something different. And a machine thinks that this should be labeled as an ostrich. If you label this as a hen, then a computer thinks that you have labeled it wrong. And if you train on this image labeled as a hen, it's as if you're training on an image with an incorrect label. And that's bad for the performance of a classifier. So if you take these kinds of perturbed images and we label these, you label this as a hen, a human might look at this data set and think all of these images are fine. There's nothing wrong with them. They're all labeled correctly and they all seem to be just fine. The perturbations made them are very small. But yet if you train on images like this, you get very poor performance for a neural network. So this is an example of doing this with CFAR. In our paper, we go through doing this with ImageNet also, but we can experiment with more architectures on CFAR just because these experiments run really fast. But with a ResNet 18, you get 95% accuracy if you train on clean CFAR images. If you train on these perturbed images that to me look identical to clean images, if you train on these perturbed images, because of a human, the images look fine and they seem to be labeled correctly. But if you train on them, then you actually get very poor performance. So if you use adversarial examples crafted on ResNet 18, then you only get 6% accuracy if you train on those adversarial examples with ResNet 18. And that's actually worse than a random guess. This is CFAR 10, so 10% is a random guess. If you craft your adversarial examples with ResNet 18, but then you train a different architecture, it actually still is pretty effective. So VGG 19, we get 11%, GooglyNet gets 7%, MobileNet gets 6%. It's actually very difficult to train on these kinds of adversarial examples. And there's been some very recent work that came out that's showing that processes like adversarial training can subvert some of these poison effects. But even with those kind of training regimes, you tend to get very low performance out of models that are trained on these kinds of adversarial perturbations. Okay, so that's an example of something that you can do to prevent information from being used to train a machine learning system. But sometimes the machine learning system has already been trained, and you still want to be able to subvert the system. That's something that happens, for example, in face recognition. So face recognition systems, they typically work with Siamese nets. And the way that they work is you have a gallery image. So this is like an image that Clearview might scrape from the internet. You have gallery images, and you push these gallery images through a feature extractor network that is pre-trained. So it's already trained on data. If I wasn't able to poison that original data set, then there's nothing I can do once that has been trained, or at least not to affect the parameters of that model. So you push a face image in the gallery through this feature extractor, and the feature extractor is designed so that images of the same person lie very close together in feature space. So all the images of Baby Yoda lie in similar regions. And so these are the images scraped from the web that end up in the gallery. And then in the future, maybe you acquire some security footage that contains Baby Yoda and you want to know who that is. So you crop the face out, you push it through a feature extractor, and it lies in this location in feature space. Then you do a nearest neighbor matching, and you can identify who this person is. So we created the system called called Loki. What Loki does is it makes adversarial perturbations to your images before they go online, so that if they get scraped by an organization like Clearview and put into the gallery, they lie in very strange locations in feature space that can't be mapped back to the correct identity. So if these perturbed images end up in the gallery, they lie in very strange locations in feature space. And then when an unperturbed image comes along from something like security camera footage that you don't have any control over, that image gets mapped to your identity region in feature space, but that identity region could potentially be empty because the social media images that were scraped were perturbed, and they lie in very different locations in feature space. So in order to create these perturbations, we solve an optimization problem that says, I want your image to lie in a different location in feature space, but I also want the image to be close to the original image in a visual perception metric. So we've used this LPIPS metric, which measures how similar the perturbed image looks to the original image. And when we create these perturbations, we also create perturbations that break a whole bunch of different classifiers. They move your feature vector around with respect to many different face recognition systems. And we look at systems that use both arcface and coastface, and that use a variety of different backbones. And we ensemble over a variety of different image distortions, like small blurs, JPEG distortion, image cropping, in order to create a system that can resist the pre-processing steps that might happen inside of a commercial face recognition system. So we do most of our experiments on this MS Celeb 1M dataset, so a million celebrity dataset. So here's some examples of perturbations. On the top, you have clean images, and on the bottom, we have perturbed face images. And we don't claim that these perturbations are invisible. Unlike the untrainable examples we were doing before, we need to make large enough perturbations here that sometimes these perturbations end up being visible. Now, for low resolution images, oftentimes it's very difficult to perceive these perturbations, but for higher resolution images, it can be easier to perceive these perturbations. But using these kind of perturbation methods, you can actually create things that are fairly effective against commercial systems. So we don't have access to the model that's being used at, say, Amazon Recognition. The Amazon Recognition API, that's their face recognition API. If we upload the Celeb A gallery, and then we try to match images to the gallery, so what we'll do is we'll choose an identity in the gallery to be passed through this low-key filter. So we filter those images, and then when a clean image comes along at test time, we see whether or not Amazon Recognition can match it to the gallery. And we find that using these low-key filters degrades the performance of Amazon Recognition from about 93.7% with a million identities, degrades it down to about 0.6%. But that's assuming that you're just doing a top one guess. So it tries to figure out the closest identity match. If you give it 50 guesses, and actually Amazon Recognition outputs the top 50 matches, if you give it 50 guesses, that accuracy rises to 2.4% accuracy. The Microsoft Azure face recognition API is a little bit weaker than Amazon's. It gets 90.5% accuracy on the Celeve data set. And it only gives you a top 1 match, but we can degrade the accuracy of this down to about 1/10 of 1% using these kinds of image perturbations. All right, so I said I was going to pause and change topics at one point, and this is the pause. If anybody has any questions they want to ask about adversarial example stuff, feel free to ask me now, and I'm going to move on and talk about some different things.
Hi, I have a question.
Go ahead.
Yeah. So first of all, in the cloth, in the very beginning, when you talk about the cloth, the pullover that you wear, that patch looked very close to a natural image. I would expect if you just backprop gradients to it, it's going to look something like a random texture.
Right. The reason it looks like a natural image is for a couple of reasons. One is that, so you think of adversarial examples as being just kind of like random fuzz, right?
Yeah.
But oftentimes that's because you haven't done enough ensembling. So for example, let's say you want to create an adversarial perturbation for an ImageNet classifier, but you want that adversarial perturbation to survive random crops. Very often you'll actually get an interpretable adversarial example. So something where it has like interpretable textures. So maybe you want to make a bird into a fish. What you might find is that the adversarial pattern you get, if you look at it, it has kind of fish shapes in it. And that's especially true if you also ensemble over different classifiers as well. If you want to find really robust adversarial examples, it's actually often the case that you'll find these sort of interpretable structured patterns. And that seems to be what happens here. Now, you might look at this and think, well, it looks kind of like people holding umbrellas walking through a market. That's what I think it looks like. And you might think that has some particular interpretation, but it actually turns out that if we find images from the internet of people holding umbrellas walking through markets, they don't have any adversarial behavior. So there's still something really specific about this particular combination of shapes. It also turns out that the image that you get really depends quite strongly on what the backbone of the network is. And I find this to be really interesting. If you change the backbone, you'll get a completely different image. For example, with some backbones, we get one almost looks like stoplights all over the image. And maybe that has some interpretation, like maybe it works because you don't expect to see a face above a stoplight, for example. But then there are other backbones we can drop in where we just get strange looking geometric patterns and other things that I don't know how to interpret.
Great. So basically, you initialize your patch randomly, and then you just do gradient descent on it, and that's what
exactly.
I see. Exactly. And this pullover, if I put, as you said, the different backbone, I will detect you. Correct? It's only for YOLO, optimized for YOLO.
If you actually read our paper here, Building an Invisibility Cloak, the paper actually focuses on transferability across detectors, and it turns out that some detectors you can get really good transferability. For example, if you train on YOLO 2, you get really good performance of the perturbation on YOLO Mini, but you might not get good performance on something like mask RCNN. Mm-hmm. And so we find these perturbations do transfer across detectors sometimes, but there are certain pairs of detector architectures where the transferability is really high, and there's certain where it's very, very low.
Thank you.
Yeah, and you might think that there'd be very strong structural similarities between the detectors that it transfers between, but actually that isn't always the case. And I don't have any good explanation for why, when it transfers and when it doesn't. It's just sometimes it does and sometimes it doesn't.
Got it. Thank you.
Yep.
There's another question if you have.
Yeah, go ahead.
Hi, can you hear me?
Yep.
So from my understanding, when you are training your adversary, there has to be some model being the target of the attack, right? And I'm wondering, how is your adversarial performance sensitive to the selection of that target model?
So which system are you asking about? I talked about a few different things. Or are you asking about them all in general?
The model in general.
Well, so I think what you're asking about is like, nothing that I presented here is a defense. Everything here is an attack, right? Now, when you create a defense, you usually have to create the defense against a very particular attack model. And very often, the defense that is very strong against one attack will completely fail against another attack. In fact, one of my communists.
You talk about you talk about you're trying to poison some face images to prevent face recognition, but suddenly, like if they change their face recognition model, then you have to train the adversarial model like all over again.
So this is what's called a black box attack, which means that we don't actually know the system we're attacking. So what we do is we create an ensemble of different academic face recognition models, and we come up with perturbations that break all of them, and then we hope that it breaks Amazon's system. Now, Amazon's system is using some face detector that we don't know. So when you give it a face image, it actually detects the face and crops it. We don't know what face detector it's using. We don't know what cropping algorithm it's using. We don't know what interpolation algorithm it uses to if it resizes the image after it's been cropped. I don't know what neural architecture it's using. I'm pretty confident it's not identical to one of the academic architectures, because you could probably improve this a lot by architecture searching. I don't know what data set their system was trained on, right? But you still get pretty good transferability, even without knowing the system. Oops. I guess what I'm trying to say is this: if they just change to a different system, I still think that this attack would be fairly effective. It's already effective against a system that we have no white box knowledge of. If they choose a different black box system, I think it would still be quite effective. I will point out, though, that there's a few things worth noting. One is that against a white box system, if we knew the Amazon recognition API, I'm pretty confident that these numbers would be 0%. But because we don't know exactly what system they're using, the transferability isn't perfect. And so we get things that are, maybe 1% accuracy instead of 0%. But that's a big difference. And the other thing to note is that if they wanted to, they could adversarially train their system to resist adversarial perturbations. And that would increase the accuracy a lot. But there would be a trade-off. When you adversarially train, you gain accuracy on perturbed images, and then you lose accuracy on clean images. So they could adversarially train in order to resist these kinds of attacks, but then they would be degrading the accuracy of their system on non-perturbed images, which is something that I think they're unlikely to want to do.
Okay, thank you. That makes a lot of sense. And I think the trade-off you mentioned is related to Billy's question. So I'm gonna let him.
Hello, can you hear me?
Yep.
Hi, so my question is, knowing the trade-off between adversarial training and the clean performance, what is the way you think it's going forward? Is it randomized smoothing or deriving some convex, relaxation bounds that are proven to be not that scalable? So I want to know your take on this.
That's a good question. I think so. I'm not sure what the way forward for what.
For defending these type of what is the balance between trading off like adversarial training performance and then the clean performance of non-adversarially trained models, like as we can see on GitHub of a Marjorie lab, right? Like if you adversarial train on ImageNet, you lose about 30% of the accuracy. That is a significant drop. So
yeah. Right. So if you look at the benchmark numbers, those people are not necessarily trying to maintain clean accuracy. They're just trying to get the best robust accuracy possible. And so those don't necessarily represent an optimal trade-off. There's been a bunch of work. My lab has this method called instance adaptive adversarial training, where we try to get a much better trade-off between robust and clean accuracy. And that's not necessarily state of the art anymore. There's a bunch of work on this stuff. You're trying to get better trade-offs. No one seems to know how to get, it seems like there's sort of an inevitable trade-off. In our instance adaptive paper, we actually give examples of reasons why there sort of has to be a trade-off. There's always going to be a trade-off. The question is how severe it is. And I don't think we really know right now what the limitation of severity is. And some of the things you mentioned, you can use like convex relaxations or randomized smoothing. I don't think that those come close to getting, those are, certified methods that have mathematical guarantees, but against certain kinds of attacks. But I don't think that those are the most practical solution, because you can come up with attacks that break those defenses, even though they're certified. You just use a different threat model. And also those don't necessarily get an optimal trade-off between clean accuracy and robustness. So right now, I mean, the best things we have in practice are just sort of hacks. They're like hacky methods for training, doing adversarial training and using various regularizers to try to prevent from losing clean accuracy. But even still, there's usually a significant clean accuracy loss. I'm just saying that the clean accuracy loss for state-of-the-art methods is not as bad as it appears to be if you look at, say, like the Modulab benchmark numbers. But I still think it's probably bad enough that I don't think it's appealing for a company like Amazon to do something like adversarial training. It seems unlikely, given how competitive they are with their peers, to have the really high accuracy numbers they can report. I think it's unlikely that that they're willing to do that. At least that's my sense.
Thank you.
Yeah. All right. There might be some more questions in the chat. I can't see the chat right now. I'm actually, just in the interest of time, because we started late, I'm going to move on, but I'll stick around at the end and after 1 o'clock. And if you guys want to ask questions, I'll be happy to take questions then. Okay. So I'm going to tell you about some of the work we're doing on what we call deep thinking systems. So there's basically two types of thinking, at least in a very simple breakdown that some cognitive psychologists like to use. There's what's called fast thinking, or type 1 thinking, and that is pattern recognition. So you look at a dog and you say, that's a dog, a chair, that's a chair. Those are pattern recognition problems. And then there's what's called type 2 thinking, or slow thinking, and those are chained logical reasoning problems that require sequential logical thoughts. So things like, how do you solve a maze? How do you prove a theorem? Right? Theorems cannot be proven just by pattern matching. They require a chained sequence of sequential logical steps to achieve the solution. Machines are better than people at type 1 thinking. They are better than people at pattern recognition. On many computer vision benchmarks, they surpass human accuracy. And if you can, especially if you look at certain specific cases, for example, recognizing camouflaged people or camouflaged animals, machines will surpass humans by wide margins, right? So when it comes to pattern recognition tasks, I think it's fair to say that computers are at least as good as people, probably much better than people. But there's something that computers are still really bad at, and that is logical reasoning. So computers are not able to do slow thinking. So things like proofwriting, causality determination, handling domain shifts. You have to extract causal variables from a scene in order to handle domain shift well. These are things that computers just handle poorly. Now, in a classical theory of mind, humans are able to solve these sorts of slow thinking problems by using using chain logical reasoning. And so in these classical theories of mind, these computational theories of mind, a problem is embedded into the brain's working memory. So you form some representation of a problem in your mind. And then there's something called the central executive, which is sort of like an abstract notion of the rest of the mechanisms in your brain. And they manipulate what's in working memory over time until they're able to solve a problem. But this concept of working over time is really important. If I give you an easy theorem to prove, you could prove it quickly. If I give you a hard theorem to prove, you might still be able to prove it, but you're going to have to think for a longer amount of time because it takes more sequential reasoning steps to find a solution. And so what we'd like to do is build machines, build neural networks that are capable of solving these sorts of sequential logical reasoning problems. And one way to pose this problem of how do you build such a machine is the question, can you learn an algorithm? So computers can actually solve certain kinds of logical reasoning problems. And sometimes they can scale those solutions to problems of arbitrary complexity, but usually we can only do that through algorithms. For example, a sorting algorithm can solve problems of arbitrary size just by thinking for longer. So by doing more computation, you can scale up the ability to solve those sequential logical problems, so discrete reasoning problems, by thinking for longer. And so one way to pose this question is, can you learn an algorithm? Can machine learning systems generate algorithmic reasoning processes that can scale up to discrete search problems of arbitrary size? So if you only pay attention to one slide in this second half of the talk, here's the one to pay attention to. Here's the idea behind these thinking systems. We're going to build recurrent networks that can run for as long as they need to in order to solve a problem. At train time, we're going to train these systems by giving them easy problems. So we'll train them on, for example, small mazes, and we'll train them to produce solutions to small mazes using only 30 recurrent iterations of the network. Then what we're going to do is we're going to try to measure whether they can perform logical extrapolation, which means that you give them a more sophisticated logical reasoning problem, and you see whether they're able to solve it, but you're going to give them a higher compute budget. So you'll let them think for longer. So we'll let those recurrent modules run for, say, 3,000 iterations. And so at train time, they only see easy reasoning problems, and they only see very small numbers of iterations. So they have a very short thinking period. After the model is trained, we then see whether they can perform logical extrapolation and whether they can solve harder reasoning problems than they have ever seen before just by thinking for longer. Okay, so how could you build such a system? Well, the first thing that we need to do is we need to replace feed-forward computation with recurrence. If I want to build a system that can compute for as long as it needs to solve a difficult problem, then it needs to be a recurrent system, so I can keep applying those reasoning modules over and over again until it finds a solution to the problem. A classical feed-forward network, where all of the layers are different, is limited in the complexity of reasoning problems it can solve because of its depth. For example, if you wanted to solve a logical reasoning problem that requires more than 18 sequential thoughts, 18 sequential logical steps, then it is not possible to solve that problem with Res Net 18. And it doesn't matter how much you train. No matter how you set the parameters of Res Net 18, you cannot solve logical reasoning problems that require more than 18 steps. And so what we're going to do is we'll take these feed-forward networks where all the layers are different, and I'll replace this with recurrent computation. So I'm going to have a first layer of the network that's like a feature extractor. It extracts a representation of the problem and sticks it into working memory. Then I have this recurrent module that's like the central executive. So I'll apply this recurrent module to the working memory over and over again, and I'll let it manipulate and work with its representation of the problem. And then finally, when it puts its hand up and says, okay, I'm done, I have a solution, then we run this solution extraction layer that pulls the solution out of memory and gives us a representation of what we think the solution is. And interestingly, you might think that there'd be a big sacrifice replacing feed-forward behavior with recurrence, but it actually turns out that if you take image recognition networks, you take image classification networks, and you just tie all the parameters together in every layer, you get almost the same behavior with a recurrent network as you would get with a feed-forward network where all the layers are different. So this is taking networks of different depth and comparing the accuracy you get if you use a standard feed-forward network, which is in blue, versus a recurrent version where the parameters of every layer are identical, which is what we show in orange. And what you see is that the same, for different architecture types, the same sorts of trends between depth and accuracy are observed regardless of whether you use feed-forward computation or recurrent computation. Even these sorts of non-monotonic behaviors are basically identical between the two. So interestingly, you don't seem to lose much when you do deep learning with recurrence instead of feed-forward computation. So the next thing we need is we need a way of controlling the hardness of a problem. I want to be able to train neural networks on easy reasoning problems and then see whether they can perform logical extrapolation and figure out how to solve harder problems after they're trained. So to do that, we need to control the hardness of a problem. So here's an example of a problem that's easy to control the hardness for. Let's look at procedurally generated mazes. So I'm going to give the network a randomly generated maze, and it has a randomly generated start point in green and an end point in red. And then when we train the network, we're going to train it to reproduce these solutions to these mazes. So we're going to supervise it with the labels of these segmented out solution paths to these mazes, and the network has to learn to solve them. And we're going to train only on these small mazes, and then we'll see if at test time the network can figure out how to solve hard mazes. What's interesting, though, is that if you just train with feed-forward architectures, let's just try training feed-forward networks on easy mazes, and then testing them on the same mazes. what we find is if there's no domain shift, so you train and test on the same data sets, the size of the maze that you need increases. So for small 9x9 mazes, we need about 20 layers to get 90% accuracy. But for 13x13 mazes, we need about 36 layers to get 90% accuracy on that task. So the bigger the maze is, the longer you have to think. And I think that makes sense. There's more logical steps that take place in solving a more complex maze. There's more branches and more steps you have to get through. But the question we're curious about is what happens if you let the system think for longer? Can neural networks exhibit logical extrapolation behaviors that are more similar to what a human has, right? A human, you can train it to solve easy tasks, and then by thinking for longer, humans can extrapolate to solve much more sophisticated logical reasoning tasks. Can a computer do the same thing if you let it think for longer? So in this experiment, what we did is we train only on 9x9 mazes, and then at test time, we show the network 13x13 mazes. Now, if you on 9x9 mazes, a feed-forward or a recurrent system can both get 100% at test time. If you train on 9x9, you can solve 9x9. But here we're training on 9x9 and testing on 13x13. And this horizontal line represents the best performance we can get with a feed-forward network, and this is architecture searching over different depths and widths of the feed-forward network. The best we can get is about 25% accuracy. But a recurrent network, if you test it with the 20 iterations it was trained with, it actually gets about 50% accuracy. And then if you let it think for longer, so you let it run for even longer, so you run more test time iterations, you'll see that the accuracy rises, and you can actually solve about 20% more mazes just by thinking for longer. So the network seems to exhibit logical extrapolation. But that's not a very impressive logical extrapolation, right? I mean, being able to solve 13x13 mazes, that's great. We can't even solve 100% of them. And so we thought maybe this was the best that we could do. And then we figured out that there's some problems with these systems, and we can make changes to the neural architectures to build neural networks that are really effective at solving these kinds of logical extrapolation tasks. So one of the architecture improvements we did is what we call recall layers. A recall connection is just a skip connection between the input layer of the network and all of the recurrent layers deeper in the network. The reason this is important is because every time the network picks up the working memory, works with it, and writes back to the working memory, it introduces a little bit of error. It has to remember the problem it's trying to solve, but you're essentially making a copy of the problem and writing it back to memory every time the network thinks. And so you're making a copy of a copy of a copy, and once you've done that 30 times, 100 times, you lose a lot of important information. Having skip connections between the first layer and all of these intermediate recurrent layers prevents the network from being able to lose information. Any information that's lost can be regenerated using the skip connection from the input layer. And then we also use something called incremental training, where we do a forward pass, and then on the backward pass, before we compute the backward pass, we randomly delete some layers in the network. And the reason why this is important is because I don't want the network to learn layer-specific behaviors. I don't want it to learn, for example, this layer knows it's the third iteration. I don't want it to learn to encode a counter in the feature map. And then when you get to the third iteration, it looks at the features and says, we're on iteration 3. I'm going to do the iteration 3 behaviors. And then on iteration 4, the recurrent module says, I'm iteration 4, I'm going to do the iteration 4 behaviors. You don't want that, because once you get to the end of the training steps, you only train with, say, 30 iterations, it's not going to know what to do if it has to think on iteration 31. And so by randomly deleting some of these layers before backpropagation, we basically make it so that it can't identify what layer it's supposed to be computing at. It can't learn layer-specific behaviors anymore. And what we find is that with the conventional systems, without these architecture modifications, we get what's called an overthinking problem. So this is training on 9x9 mazes and testing on 13x13 mazes. Now, if we train on 9x9 and test on 13x13, we'll eventually figure out how to solve those larger mazes if we think for long enough. So if we run about 30, 40 iterations, these conventional networks, which are dotted lines, will solve most of those problems. But if we keep thinking for longer, the performance will fall apart. So it overthinks and it degenerates. Whereas with these architecture modifications, the performance just increases to 100% and it just stays there seemingly forever. So we can just run these architectures as long as we want, and we'll just keep improving performance on these sort of reasoning tasks. So this is going from 9x9 to 13x13, but you can go even bigger. So once we get up to 59x59, so we're still only training on 9x9 mazes, if you ask these systems to solve 59 by 59 mazes, what we find is that all feed-forward architectures that we can find and the naive recurrent networks, there's this dotted line here at the bottom. All of these architectures get 0% accuracy. So even training a very deep feed-forward network on 9 by 9 architectures, it's not possible to get it to solve a 59 by 59 maze. It just can't make that logical leap. It's too big of a domain shift. But using these kinds of architecture modifications, you can actually solve those things very easily. But I'll point out that we are training using only 30 iterations. And then at test time, if you run 30 iterations, you get 0% accuracy, even with these recurrent modules. But if you let them run for, say, 500 iterations or 1,000 iterations, even though they only ever saw 30 iterations at training time, if you let them think for much longer at test time, they'll eventually perform logical extrapolation and figure out how to solve these more complex problems. So one of the questions we have is, how much can you scale this sort of behavior up? So we'll start with a simple problem. This is a problem that can be solved with a for loop. So the input to the network is going to be a sequence of bits, and the target that it has to predict is the cumulative sum mod 2 of those bits. This is called the prefix sum problem. That's been studied a lot in the machine learning literature. And we're going to train it on short sequences and then see whether it can generalize to large sequences. But this is an easy problem. Like I said, you can solve this with a for loop. There's no logical branching that has to happen. If we train on 32 bits and test on 512 bits, we find that these systems, they can solve the 512-bit problem. We train them for 30 iterations. And if you test on 512-bit problems with 30 iterations, they get 0% accuracy. If you let them run for long enough, once you hit about 100 iterations at test time, they start to get non-zero accuracy. And if you let them run for long enough, they'll actually solve 100% of these larger problems just by performing logical extrapolation. So that's an easy problem, right? What about a problem that requires if-then? So it requires branching, and that would be something like these mazes. So we train on these little 9 by 9 mazes. And what we find is that only by training on 9 by 9 mazes with 30 iterations, you can then solve a 201 by 201 maze if you run 2,400 iterations. So you have to run 2 orders of magnitude more computation at test time than you ever saw at train time. But if you give the network long enough to think, it can actually perform logical extrapolation and solve this task. So here's the solution. So I asked my students, I saw this and I asked my students, what is the biggest maze that this thing can solve? So we tried to solve the biggest maze we could. Here's a really big maze. There's a green dot here. There's a red dot here. And the reason this is the biggest maze we can solve is not because it's a limitation of the network. It's actually just the limitation of what will fit on our GPU. So this is training on only 9 by 9 mazes, right? That's all the network ever saw during train time. And it only trained with 30 iterations. And at test time, we give it this 801 by 801 maze. And here's the start and the end solution. And what we find is that it does generate a solution to this maze, but you have to let the network think for 20,000 iterations. So this is 3 orders of magnitude more computation than the network was trained on. And it's solving a much bigger problem the network ever saw during training time. And this requires, the recurrent module here actually has 5 convolutional layers in it. So this is equivalent to, it's like running a ResNet 100,004. This is over 100,000 layers of computation have to happen in this network, but it's still able to generate a solution to this problem. And this systems actually have interesting error correction properties. So we try to interpret what they're doing. What we found is you can actually run the solution extractor at different stages of the process, and you can actually see the intermediate solutions that the network has. And what we find is that if you run the solver on a maze, you can actually observe what it's doing. And it turns out it's using a very simple parallel algorithm called dead-end filling. And when I figured that out, I was kind of happy and also kind of sad. I thought maybe it was doing something much more sophisticated, that it was some sort of very complex algorithm that it was using. But it seems like it's just using dead-end filling, which is quite simple. But then it turns out that these networks have really complex behaviors that you wouldn't expect. So for example, if I contaminate the solution, so in the middle of the maze solve, I'm going to fill the memory with garbage. I'm just going to add a huge amount of Gaussian noise. And then this is the solution that we get. So the memories have been wrecked. If we do that, the network will compute for a short amount of time, and then it seems to realize that something is wrong, and then it will actually dump its memory, and it will start over from the beginning, and it will solve the solution. It'll solve the maze correctly, even though you corrupted its memory halfway through. So there's some sort of very strong error correction behavior. And then if you let the maze get solved, and then we change the location of the start and the end point, so I'm going to change the location of the red and the green point, then it seems to use some sort of tree search type method to solve the solution, to solve the maze that actually reuses all of the work that it's already done. So you'll see there's actually a solution path that walks from the green all the way to the red without making any wrong turns. So we'll slowly update from both directions, from both the red and the green direction, and it meets in the middle, but it never fills in any incorrect pixels along the way. So there's some sort of more complex error correction behavior that it seems to be able to do. And then finally, let's look at a challenge problem. So this is chess. What we did is we took chess puzzles from the lead chess server, which is a server that humans play on. It has these chess puzzles where you have to look at them and you have to identify what the best move is. And we label them by highlighting the location of the piece that should move and the location that it should move to. And so we took 1 million puzzles from lead chess and we separated them from easy to hard. So they all have an ELO score that tells you how hard the problem is. And those ELO scores are generated by showing them to people and seeing what percentage of people can solve them. And so we'll take the 600,000 easiest puzzles as a training set, and then we'll try to test on 200,000 hard puzzles in our data set. And what we find is that by these sort of thinking systems can actually outperform a feed-forward network by about 25% accuracy on the hard data set. And what's interesting is you'll see the performance of these thinking systems improves continuously as you let them think for longer. And they actually gain more accuracy outside of the training regime if you let them keep thinking. So even on these sorts of chess problems, we still are able to observe that the sort of logical extrapolation occurs. The network is able to solve more difficult logical reasoning problems at test time than it was able to solve at train time. Okay, so just to wrap up, at the end of my time here. So some thoughts about thinking, some things that I think are interesting about these systems. Deep thinking systems generalize to hard problems that are outside the training distribution, and that's a domain shift. So you're training only on easy problems, and you're testing on a set of hard problems that it's a disjoint distribution of problems. Now, you might think that a network trained on easy problems would fail to generalize to hard problems because of the domain shift. And if you think that, then you are correct. So if you take a 30 iteration recurrent network and you train it on easy problems, and then you test it with 30 iterations on the hard problems, it will fail. It can't make it cross that domain shift. But if you then let it think for longer, then it can perform logical extrapolation and it can generalize to the disjoint test distribution. So it can survive that domain shift by thinking for longer. But what's interesting is that when you think for longer, you're changing the model, and that's how you survive that domain shift. The 30 iteration model, so the depth 30 model, was trained on one distribution, and it can't survive testing on a different distribution. But if we unroll it and make it a 30,000 iteration model, so now it's a deeper network than it was before, right? We've changed the architecture after it's been trained by unrolling it. When you change the architecture, you change the decision boundaries of the network and you change the model's behaviors. And by doing that, we create a new, deeper model that can solve these more complex problems. And so I think there's some interesting things going on from a generalization theory perspective. Another thing that's interesting is that these systems solve a problem. They generate an algorithm for solving a problem only by seeing the problem and the solution. They don't get any incremental supervision over what the steps of the algorithm should be. So if you show it chess problems, it will generate a stepwise algorithm for solving chess puzzles, even though you didn't give it any supervision over what should happen at every individual step. And that makes this different than a lot of work that's been done on, for example, neural Turing machines, where you give it incremental supervision over what you want the steps of the algorithm to be. And then finally, I think this is ambitious, but I wonder if thinking systems can replace handcrafted algorithms in various ML systems. So if you look, for example, at AlphaGo, right, or Mu0, which is a system for playing games like chess. All of these systems involve a handcrafted Monte Carlo tree search. And machine learning is only used to prune the tree and speed up the tree search. What's interesting is that you can actually learn these kind of search behaviors inside of the network. The network can actually learn these search behaviors end to end. So it's interesting to wonder whether you can build these sorts of game playing systems without using a handcrafted tree search. Maybe that algorithmic behavior can be learned in the neural network instead of relying on a human to craft it by hand. Okay, thank you very much. I only went 2 minutes over. Hopefully that's not too bad. But yeah, thank you very much for taking time to listen. Here's a list of papers that I spoke about if you're interested in them. And I'll hang around for a few minutes and answer questions. Sorry for going over, but I meant to start a little bit earlier. But if you're able to stick around, I'll answer some questions.